Hello, thank you for joining me today again for the second part of Venya. If you have been following up last video, I explained that Venya is just a kind of a fun project, and it's kind of like we are focusing on building a voice first AI personal assistant. And last video I talked about like the goal, the reason why this project actually started, and how we are going to approach this project. And I also said I'm going to build this in public. You would see everything. Also, this is a fully open source project, and at the end of this video, I'm going to share you the URL to the GitHub repository for this project. And yeah, so and also last video I talked about. I mentioned that this particular project will be focused fully, will be built majorly on Rust. Rust is a very, it's like, let me just say it's a new programming language, not really new, not relatively new, but modern. And I believe is the best suited for this because the goal of this project is to make sure that it can run on multiple or different devices, and performance shouldn't be an issue. So performance is very important here because you are dealing with a lot of high end high end functionalities like voice processing, audio processing, and text into speech, putting speech into text in real time. So you require a lot of a well efficient language to actually run and build this. Yeah, so let me move forward to this. This video is focused on the technical foundation for this project, and how like the basis of all, like how this is going to work really, how is it going to work. The initial idea or the initial video was, oh yeah, I want to build this. It makes sense, it sounds good, but now we need to be sure that it is possible. We need to be sure that it is viable, and maybe we are not just hallucinating, or I was not just hallucinating, right? Yeah, so let's move forward. Yeah, so as I said, Rust. If you don't know about Rust, please check Rust programming language. I think it's getting really common and is used in a lot of fields like blockchain. It's used in embedded computing, a lot of places, embedded systems, and a lot of, like it is used in a lot of very important places. And in fact, Microsoft already start like using it in house to build some of Windows um, OS, and I think it's great. So please check it out. And why this was chosen is performance, safety, and reliability. Yeah. So I always say like one thing I love about Rust is it's it can be strict. It's strict in terms of how you write. It's enforced the way you write your code, but it makes it neat, makes it very viable and safe. And I think it's great. And so that's why we are using this. But the whole focus is we want something that can run across board with just a single code base. And Rust seems like a good way. We can write it in C++ or anyone, but Rust is just great. Yeah. So let's move forward. Yeah, for Rust, the framework of choice is Dioxus. I chose it because it felt familiar. Let me go there. So it felt really familiar, I would say, and it felt really familiar, and I could like relate to it because I'm coming from a web background, so I write React, Vue, and I could relate to it uses concepts that kind of very similar to what React does and what Vue does, and I think it makes sense. And it's I don't write HTML, so with this you still write your normal Rust, but in a uh, more verbose way, in a way that is really really good. Like you are not really like maybe writing on that set of language like in you're writing Flutter and all those things. You are writing normal Rust, and you're also writing. You can always tie your project with theme with CSS. So if you I will drop the link to this documentation if you want to understand how Dioxus work. It's a great framework, and I've been using it, and okay, it's been good, and it's also easy to learn if you're coming from a web-based background. So yeah, you can check it out. So yeah, there's support for theme with CSS. If you don't know about theme with CSS, it's like if you are coming from the world of bootstrap and all these things, like bootstrap but better, I would just say it's more like instead of writing raw styles yourself, you have like a helper set of helper utility classes, and you can easily just write your own quick utility classes to design and make a better web page. So since Dizos kind of uses a web engine to render the view for our app, so it's easy for me to still like use theme to style this app without it really being HTML in codes, right? Without me writing HTML, I can still add normal styling and tests and classes using theory sensors, and which makes it easier to design and build a really robust design and experience, because I want to work what I'm familiar with, and I think that is just made that possible. And yeah, so with all this, we are still writing Rust, like still largely purely Rust. So and Rust has that performance benefit, and I think that's why this is really a great option. Yeah. All right. I would show an example of because as I said earlier when I started this project is I'm learning really. I've not used Dizos before to do any project, so I went through their documentation, learned and read through their documentation to understand. Oh, okay, this is how to use it. This is how it works, and also build some examples. So like I'll just show you an example of something. Right. Okay, I'll show you an example of something where now this is an example of a running app, and we have this is one of the demo app on Daiso's documentation, and this is an example of like Tinder for dogs, right? So hot dogs, right? And where I can easily like skip and see different dogs and maybe save them if I like them, and I can easily like check dogs. Yeah, it's simple stuff, but the whole idea is that it's actually very simple in terms that you this is Rust, this is purely Rust. Yeah, everything is Rust. These are the components. For example, this is the um, this is the views really, and this is like the source image where I'm getting the data from, like the open API for dogs where I can fetch images, and this is just me writing the views, which is the dog views, and all these things looks like I'm writing normal Rust, but it's been rendered as like a web page, and which makes a lot of sense. So I can easily like give IDs to it. I added like various tests for Tailwind CSS. So these are Tailwind CSS. I can easily just do what I need to do, and it works perfectly. Right. So and yeah, so that is it really. This will be deployed to the GitHub repository, so you can check it yourself, run through the code, and get how it works. But it is pretty interesting, right? And it works really well. So yeah, and yeah, thank you. So let's go back to the next ones. So most times, before when I start working on a project, I try to like um, yeah, so when you want to work on something, there's an idea, a beautiful idea, it makes sense, it's dope, but now you go back to the drawing board to like confirm if this is possible, if this makes sense, right? Because um, after the whole thinking, you need to actually confirm your hypothesis. You need to confirm that it is possible to actually achieve that. So, which is what this video is about. And I think the series of the next explanation I'll be giving is showing you how I was able to like come up with something that I think might work, right? Because for Venya to work majorly, there are two very important things that need to be figured out more efficiently. One is the speech to text. So if I speak to Venya, Venya needs to be able to convert my speech to text, right? And maybe that send that text to maybe an AI or a brain system that understand the text and return a text, right? So then when that text is returned from the AI, Venya should be able to convert that text to speech. So two very important things is we need to figure out that a solid way to make sure that the speech to text is fine and the text to speech is fine. So and that is a very important part of this project, and yeah, so let's move forward. So for speech to text integration, the goal is just to make sure that we use natural language processing and convert the speech that was spoken to a text. And for us to do that, we need to use an AI model. There's not going for that. They have to use an AI model for that, and not just that, because this project is focusing on low end devices, not just like your laptop. Right, we are also looking at phones. We need to make sure that the model that we need to use for this has to be able to perform on smaller devices that doesn't have like this very very large memory. So that's the end goal for this selection. And yeah, so let's move forward. Yeah, so I said model selection. There are a number of things that was done, and let me walk you through it. What I did, that's speech to text. Yeah, let me go there. So there are a number of things that needed to be done. I was looking for a lot of AI models. I'm going to drop the link for all these things, all these resources I used um, under this video. So Vox is like an offline. So also very important. We need an offline. We need to make it work offline, because the goal is that Venya should be able to work almost offline, like totally offline. Except okay, maybe I'm trying to maybe reach a third party AI LLMs, but yeah, but largely most of the voice conversion, voice um, talking, replying you back, everything is happening on your device, not sitting on somebody else's server, right? So that's the whole idea, that my data is not sitting somewhere. So everything has to work offline as much as possible. So that the goal for the models I was trying to find was, um, okay, let this be offline, and we need something that can run on your device. So when I found Vox, it makes sense a lot, and I was implementing it. But the issue with when I was implementing it was I couldn't find a Rust binding for it, or the Rust binding for it, meaning that I couldn't find an implementation for it in Rust. So I did what most developer would do, try to hack my way around it, and I think it was a bad idea. So like because I know that most of this particular model is kind of Python first party, right? The testing, the documentation, or everything is in Python. So I thought that, okay, what if I just run a Python instance in my app, right? Yeah. I don't know if you are very, very, very sound in this. You know, that's a very bad idea, because you are shipping a whole full Python instance and shipping it to your into an app. That's gigs, a lot of gig, and nobody will download an app that is that heavy, right? So, but I just left it alone to make sure that I'm able to tell you and show you this, right? So, the speech to text part, as I said, there was this part where I used Vox, but I couldn't get something that, like, I didn't get it to work with Rust. So what I did was that I created a new library in Rust that kind of prosy, like take the kind of run everything in a Python environment, even though I'm running from Rust. So right, it's kind of I take the request I need to take, and I send it to the library. Then the library runs the command in a Python environment. So that's what it does here. And yeah, I'm going to delete it later, but just to show you that yeah, that can work also, especially if you maybe this is not actually going to be an app. It's maybe going to be a backend system that is going to just send APIs to a front end. So I think this works perfectly, right? But that's not our case. So yeah, so the text to speech, this is the code. As I said earlier, this will be on on GitHub, right? So there are two parts of it. So let me go to Orthodox. So this is the demo. I'm going to go to this page to uh, to demonstrate this. Yeah. So these are experiments. As I said, yeah. So we are currently focusing on speech to text, right? And I think what I can do is to just let me check the code here. So we have these, we have components, then we have speech to text. Yeah, exactly. So here is it. Now I want to test this speech to text, meaning that I want to record something and see. So now in this code, I have this particular function that says convert to text, meaning that I will record something, then after recording it, I want to convert that particular speech to text, right? So this actually does it, right? So I have two parts. So I have two models I'm using. Okay, let me finish that. I have two models I'm using. Yeah, Vox and then Whisper. Whisper is majorly written in C++, but thankfully there was a Rust binding for it, so there was like a Rust package I can use to like use it, and which makes a lot of sense. So and it was faster and better. So yeah, so there are two models, Vox and Whisper, for the speech to text. And for Vox, I had to use like Python. So one thing I can do is this. I'll comment this, because I want to test how Vox work. So let me comment out that for Whisper and check it out with. Yeah, so to the speech to test, let's just test Vox and see how Vox works. Implementation has been done, so let's check it out. For Vox model, so here's it. Let me record something and let's try to convert the speech to text. All right, so let's go here. hmm Now let's speak. Hello, we are testing this out. Convert this speech to text. All right, so let's convert to text now. Let's see what it does. Slow a little because we are running it in Python, right? Yeah. So now this is what it said. Allow testing this out, convert speech to text. So yeah, it's sort of right, really, but it's not perfect. And then so one thing I noticed with Vox is also that like the small models are not really accurate. So if you want more accuracy, you need to like download more heavier models. So yeah, so like these are the models, for instance. So these are the these are the models here, and the models are in the Python runner. So these are the Vox model. I'm using the this one, which is the larger one, this one. So I think it's not that perfect, but I think it works, right? So and it works offline, which is beautiful. So that is for Vox model, and I'm not going to go forward with it because obviously I couldn't run it directly in Rust, so I need to like use Python, all those things. Yeah. So, but just wanted to show that to you, and let me comment it out. Run Whisper. So Whisper is written in C++, and there's a Rust binding, so it's directly written in Rust. Most of the implementation is written in Rust. So let me save and see if everything is fine. The same audio we recorded earlier, we are going to see what Whisper will say or would extract from that if it's been more accurate. Yeah. So let me close this and we run. All right. Okay, let's go here. Okay, so now let me convert the same audio to text. So let's see what it does. All right, beautiful. So this does a better job in saying hello. We are testing this out, converting this speech to text. Yeah, like it works really better than Vox, and then it's also lightweight, better and faster. So the way this is going to work in real time in when we are using Venya is that as I'm talking, for instance, as I'm talking now, we will be recording this audio in chunks and then sending it to this particular model to convert it to text and then converting it in real time. It's very 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 fast because we're not sending a lot of audio file at once. We're converting it to chunks and then converting to text in real time concurrently. It makes sense a lot, and I believe that Whisper is the guy for us for text to speech. Yeah. So here is it. Yeah. So let's go to the next part, which is speech to text. Yeah. So as I think the goal has been achieved. We want to choose the best open source model. Both Vox and Whisper are open source models, and I believe Whisper is actually very performant. It has a very good memory usage, and the goal has been achieved because it runs offline, totally offline, and is real time, close to real time. Yeah, because when we start to run this, we are running it in the background, and we are running a lot of processes to convert it in real time concurrently, and it will make a lot of sense. Yeah. So that's the speech to text integration, and that I think is okay. Yeah, for the text to speech, this one is tough, really tough. Oh my god, really tough because um, it takes a lot for AI to be able to like convert spoken like text to word and speak it like a human will speak it. Like I don't know the code where I saw this code, but it's kind of like things that are so easy for human to do, AI for computer finds out to do, right? So I think that's just a normal sense of how all this looks like, right? But it's very tough to achieve this because you need high performance, you need something that is going to work without you needing a GPU, right? To convert it. Also, you need something that is not sounding like a robot, that sounds human, and achieving that is really tough. But yeah, so a lot of experimentation was done with this. Initially, when I started, I used this YouTube presentation, like a presentation from Rust Nation 2024 by Daniel Mike Kenna, about speech to text written in Rust purely. And I think this is a very good resource if you want to fully understand what's happening here in the Venya code base, right? Because this is actually what I use to understand and approach this particular implementation. And there's also like a GitHub repository for that. I'm going to drop these two links under this video. Um, yeah, so this is the GitHub repository, also explaining and giving you access to a lot of all like the slides, the resources, the code, which is also part of even the code I push for Venya, for text to speech written majorly in Rust. This makes sense, and but some things I recall that some things they are out of date, they are not what it seems to be again, and some of the implementation are they are kind of better implementation at the moment. So yeah. So the major idea of text to speech is that as I'm speaking, sorry, from text to speech is that I gave AI a bunch of text. Right now, AI doesn't know this text, right? But I need to convert it to something that, like, I want to allow the computer rather to actually speak this text out. For computer, it's just a bunch of code, right? Just a bunch of strings, right? So AI doesn't cannot pronounce it. So first, you need to like convert this text, like this spoken normal written text, into a spoken text, right? A kind of phonetic manner of like representing a particular word or a group of sentence that is written. Now we convert that written text to spoken text. Then after that, converting to spoken. From that, we convert the spoken text into chunks of normalized chunks, right? So, for instance, I'm trying to pronounce system. System is like it has its own like phonetic way of being pronounced. It has its own grapheme. It has its own phonemes. Like it is a word, but it is made up of multiple sounds to make it form system, right? So, ability to convert and break down these words into chunks, and then also words or sentences are just more than words. Also, we have punctuations, we have a lot of things, context to it. Like also we also have like things like after I've converted it, how do I also like uh, after I've converted this text to like words or like spoken words that I can give the computer, how will the computer know how to pronounce it? So after text normalization, then what happens is that we generate a set of spectrogram rather. So spectrogram is more like a plot of the frequency and amplitude of the pronunciation over time. So like it's like you're talking, you see all those graphs when someone is talking, yeah. So kind of convert it into that. So every word has its own frequency and magnitude. Every phoneme, every grapheme, every sound I make has its own frequency and amplitude. So converting it into something like that to generate a spectrogram. Then from that spectrogram, we can now take that spectrogram, which is just a bunch of frequency and amplitude, take it and give it to something that was now going to pronounce it based on the frequency and amplitude data we have, right? So convert it into an audio. So that's what the vocoder does. I don't think I'll do it. I'm doing a very good job explaining how this works. If you are very interested in how this works, please I'll drop the link to the video for that presentation. So a vocoder is more like converting those frequency and amplitude into voice, into words, and then and most times too there are a lot more to it, because it's not just also speaking the sound. It's also like intonation, pitch, rhythm, accent. So you can have different accents from different people. The way I will speak English as an African is different from the way an Indian will speak the English. So it's not just the sound, it's also the intonation, the pitch, the yeah. So there's a lot to it, and yeah. So um, for me, I used a number of resources. It took a lot of time, and I used a number of resources. Majorly, I started with this Rust presentation. You can check this repository out. Then after that, I so it was I did make it work really. So but it was not perfect. So I'm going to run a sample to you. Was not like exactly what I wanted. Then after some time, I continued making my research, and I found this guy. They call themselves. It's this guy. I think it's Kokoro. Let me see, Kokoro RS. Yeah, Kokoro AI, which is an open source AI. It's free text to speech, right? And it's actually very fast. It works very well. They have different voices. They have different voice. Like they have different accent, different voice, and it's really like it's not just English. Also different country, different languages, which makes a lot of sense. And there is luckily for me, there was a particular Rust binding for this particular model, right? So there was a particular, yeah, this Kokoria exactly. So you can check it out. I'm going to drop this also. It's a lightweight model that was trained with just 82 million parameters, but it's very fast, very performant, and I was able to use it, right? And but I used through Sharper Onyx. So like this one is also like a Rust binding for speech technology for speech models. So this one does speech to text to speech, a lot of things. Just like kind of um, like a pathway to access other models. So that's what this does, and this makes a lot of sense, and it made it possible for me to like access the models from Kokoro, and it makes a lot of sense. Yeah. So I'm going to show the demo of the progress, and yeah, let's go. All right. So I did try to. So for this, yeah. So this is the demo majorly, and for this demo, I'm using Kokoro directly. So for using the one where I use Decathlon, I use iFi GAN, a lot of processes like those ones, the code is still sits on this repository, which if you're interested in it, you can go through it. It works, it generates an audio, but it doesn't sound well. So it doesn't sound really human. It sounds like robots, right? And I try not to go forward with it. So I settled down with Kokoro, which is like a model that can easily run offline, and it's actually fast enough to do what needs to be done. So this one has a lot of voices. So you can set the voices. We have female voices, male voices. We have voices from okay, British English, American English, Spanish English, French English, right? Chinese English, yeah. So various accents are present here, and it makes a lot of sense. So I'll run a sample for you to see this, and yeah, let's see. So let me run speak test. So yeah, so it is speaking. So like the thing is, I'm going to, so currently it generates an audio file. So I'm going to like open the audio file. I think the output audio Kokoro exactly. So let me open this in the review, and let's run this and see how it sounds.
Venya is a voice first AI assistant that listens, learns, and grows with you, helping you manage your day, reflect, read books, and spark conversations. Venya is a voice first AI assistant that listens, learns, and grows with you, helping you manage your day, reflect, read books, and spark conversations.
Yeah, yeah. So this sounds so human, sounds so real. I can't walk through the code for with you because it's a lot of processes. And what I'll just say is I'm going to push this repo so you check it out yourself. And the this let's try a mail. Let's try a mail voice. Let's see how that sounds. So let's speak test. Alright, still starting. Yes, it's done. All right, so let's go back to this. Let's see exactly. Let's run it again.
Venya is a voice first AI assistant that listens, learns, and grows with you, helping you manage your day, reflect, read books, and spark conversations.
Yeah, great. So that is just a sample, really, and this is an example. I think this example was from the normal one using iFi GAN. iFi GAN is a vocoder, is a vocoder model that converts MEL spectrogram to audio file. More like after generating those spectrogram, then you need to convert it to voice. That's not using Kokoro, using another model of doing the process yourself. Then you can convert that mail spectrogram into spoken words. So I fi GAN, I found it and I said, okay, this will work. And it was not that I recorded this one I'm about to play. And I think it actually works, but it's just that it's only one voice I could generate. So I just left it alone. So let me play it. It's saying,
Hello, I hope you are doing awesome.
aha.
Hello, I hope you are doing awesome.
Yeah, so if you notice, it sounds somehow, it sounds real, but not that real. And this is the only voice I could generate. So I stopped there, but yeah, that's it. So um, let's. I think that's all. That's all really. You have access to this, so yeah. So yeah, for the text to speech, I said yeah, open source. Both Kokoro and all of them, all the models I tried were open source, and voice quality. Yeah, that was very important for me. That's why I stopped using iFi GAN and the whole process of using trying to build the whole pipeline myself. So I stopped that, and because I found Kokoro to have a better voice quality and more languages, more support for ancient assets, which should be very important for Venya because people using it around the world, you want to set your voice, you want to set the kind of assets accent you want to actually hear your personal assistant speak to you. So I think giving that ability is actually a good plus, and yeah, so we just want something realistic. We want something friendly, so I can set the tone, I can set the voice. Yeah, we want something good. So yeah, I think we have been able to achieve that with this text to speech integration. Yeah, so this is more of like a rough state we have now, right? With Venya, more like the repo is there. It's more like yeah, I think the basic idea of Venya is going to work. I think it's going to work really because those important things I was not sure of before, like can I convert speech to text and text to speech directly on my device at a very good speed without needing GPU. So I think that is possible now, and yeah, it now depends on how well we can actually like structure the system that even though those processes are happening with the AI, it is actually having a good experience that the user is not really bothered about what is really happening underneath. All right. So next part is the user interface. In the next video, I will review the UI UX design for Venya. I came up with that rough idea, but I'll review that. And by next week also, it will have a UI. So Venya will have a UI that we can show, that I can show like, oh yeah, this is how Venya is going to look like. This is how Venya is going to work. And after for the next video also, Venya needs to now communicate to an LLM, like a large language model. Naturally, I've been thinking of this that yeah, for these language models, we have those that can run offline, but they are not powerful enough because large language models are memory intensive to run. So most time we still need to depend on cloud-based large language models like Google Gemini, ChatGPT, and all those. So integration, creating an integration for that would also be important. And assistant feature, yeah, other things around Venya will start to take shape, right? That's for the next video, to see how this works. All right, guys, thank you for joining me for this video. Please subscribe to this YouTube channel so you can get more information about you can get to know when new video drops. And yeah, thank you very much. See you soon. Bye.